Today we're going to be talking about finding the derivative using the difference quotient. Here I've drawn a set of x and y axes, and here is any old function. Why do we know it's a function? Well, it passes the vertical line test. That means that any vertical line drawn anywhere in our function only passes through our function one time. So clearly this is a function. This here is any old point x. I don't know what that x is, but that x will correspond with some y value, which I'll call f of x. If I go forward some undetermined amount, I'll call it the change in x, signified by this delta x. Then this new point will be x plus delta x. That's our x coordinate. Therefore, this second point is x plus delta x, comma, the function value at x plus delta x. Of course, if I draw a line through these 2 points, as we remember from our time studying geometry, a line through 2 points is going to be a secant line. A secant line simply means that the line goes through 2 points. So clearly this red line is a secant line. We can find the slope of the secant line. I use m to designate slope. We know slope is y2 minus y1 over x2 minus x1. This point here that I called x comma f of x, I'll designate as x1 comma y1. And this point, x plus delta x comma f of x plus delta x will be y2. So that allows us to say the slope of the secant line is y2 f of x plus delta x minus y1 f of x, all divided by y2 x plus delta x minus x1, which is simply x. So if I clean this equation up a little bit, you can see that the x's will cancel. And so what I'll finally be left with for the slope of this secant here is m secant after simplification is f of x plus delta x minus f of x divided by delta x. This delta x has now got our attention. If we take this delta x and we shrink it, so now here is delta x between x and this new point, then our second point is here now. And when I draw a secant line through these 2 points, you can see its slope is much different than the previous red line. And what I'm going to do is I'm going to keep on shrinking this delta x. Now, let me see if I can shrink that for you. If I shrink this delta x down to size, let's go with black here. If I shrink this delta x down to size, now here is my delta x. Nay, let's make it smaller. Let's make it so small that this second point virtually sits right on that first point. And if that happens, then our secant line, as we know from our time studying geometry, a secant goes through 2 points when we intersect it with a circle. A tangent line from geometry only intersects at 1 point. So as we decrease our delta x, we're going from a secant line to a tangent line. So the tangent line to our graph, which I'll draw in green here, is just going to kiss our graph at one spot. We say tangent lines are very, very romantic. So here is m tangent. Well, that's our tangent line. We want the slope of that. What did we do to make a secant line with 2 intersection points into a tangent line with 1 intersection point? What we did is we took the limit as delta x goes to 0 of f of x plus delta x minus f of x divided by delta x. So what is this? This is m tangent, the slope of the tangent line. And we call this the derivative, and we designate it as f dash of x. So this here is what we call the difference quotient. When you're asked to find the derivative using the difference quotient, this is what you use. The derivative we've designated as f dash of x. Also common in our course, we call it y prime or f prime of x or dy dx. Dy dx is the same as y prime, is the same as f dash of x or f prime. They all give us the slope of the tangent line. Remember, a tangent line is just going to intersect our curve in one spot.